Welcome! This time we will analyze how the traction force varies during a driving cycle and explain the result in terms of how the different force components vary. We start by simulating the vehicle model over a whole driving cycle in QSS. The result in this lecture are for the NEDC cycle. When that is done, we can look in the MATLAB workspace. There we find 4 vectors with the forces in the vehicle model, 1 vector with the total traction force, and a vector with corresponding timestamps. For analysis of the power, we will also use the vehicle speed vector. First, we plot the total traction force as function of time, together with the vehicle speed profile over the driving cycle. Since the first city driving part of the cycle is repeated 4 times, we will only plot this part of the cycle, starting with the 4th city cycle, followed by the highway part of the cycle. Here we see that shorter part of the NEDC cycle. We can see that the traction force varies very much during the driving cycle, and in this lecture we will explain why the traction force varies in this way, by breaking down the force in its components and study them one by one. Here we only plot the rolling resistance force during the cycle. Notice that we reduce the Y-scale from 2000 to maximum 1000 Newton to better see the rolling resistance force, as it is much smaller than the peak value of the total traction force. It can be seen that the force is about 150 Newton and is constant when the vehicle is rolling, and 0 when it stands still. This is the aerodynamic drag force. Like the rolling resistance, it is 0 when the speed is 0, and it increases as the speed square, which makes the force much higher at high speed than at low speeds. It reaches almost 500 Newton at 120 km per hour, while it is only 85 Newton if the speed is 50 km per hour. This diagram shows the net force on the vehicle, that is, the force accelerating the vehicle. It varies in a completely different way than the rolling resistance and aerodynamic drag forces. Notice that the Y-scale has changed back to showing force values up to 2000 Newton. The net force must be positive to accelerate the vehicle. So whenever the speed is increasing, the net force is positive. A steep slope in the speed profile corresponds to a high acceleration. To achieve a high acceleration, the force has to be high. A less steep increase in the speed profile corresponds to a lower acceleration, which requires a lower net force. When the vehicle decelerates, the net force is negative. The net force also becomes more and more negative the higher the deceleration is. At the end of the cycle, there is a braking from 120 km an hour to standstill in 3 steps. Initially, there is this deceleration, requiring this much net force. After some time, the deceleration is increased. This is seen as a steeper slope in the speed profile, leading to a higher deceleration force. At the end, the deceleration increases even more, with an even steeper slope and more negative force. When we add these 3 forces together, then we get the total traction force shown in this figure. This is the same plot we started from, but now we know why it looks the way it does. We can recognize the positive peaks during acceleration, caused by the net force, and the negative peaks when decelerating. It can also be seen that the force at a constant speed increases with speed due to the aerodynamic drag increasing with speed. At standstill, the force is 0, since rolling resistance, aerodynamics, drag, and net force are all 0 at standstill. Remember that this cycle does not have any gradients. An uphill gradient would add a force to this curve and subtract from it during a downhill gradient. Now you will have the opportunity to test yourself on determining how the traction force changed during a driving cycle, and to explain a given change in force in terms of what caused it. Notice that it is not sufficient to memorize the equations for the forces, but you should also be able to use them for this kind of analysis. For engineers, equations are very useful, not for their own sake, but because of what they can tell us about the system we design or analyze.